So we'll start with this little clicker quiz here. This is a force where objects are attracted or repelled to one another. Is it light, sound, or is it magnetism? Well, I think it's pretty obvious what it is.
With the owner of vehicle license plate number GG.
All right, Terry, Courtney, you want to take a guess? True or false? Magnets have a north-seeking pole and a south-seeking pole.
True that.
Wait. It's a trick question.
Magnets have a north-seeking pole and a south-seeking pole. True or false? Two of the same kinds of poles repel each other. Is that true or is that false? Two of the same kinds of poles repel each other. Is that true or is that false? Two opposite poles attract each other. Who said this was going to be hard?
I feel like these are trick questions. I'm getting everywhere.
Wait a second. What was the question for 3?
Two of the same kinds of poles repel each other. Opposite poles attract. True or false? Now, what about number 5? The area around a magnet that behaves like a magnet is a magnetic color, field, sound, or distribution.
You're just doing this to get our marks out.
I won't actually be recording these marks.
Oh, wow.
Now that we're doing good. One thing I need to
The further apart two magnets are from one another, the stronger the forces that attract or repel the magnets. Is that true or is that false? The farther apart, the stronger the forces. When magnets are broken into small bits, the bits themselves can become small magnets. If I were to go to the back, take out a magnet, and with my bare hands break it in half, would I have 2 magnets? Oh, I'll show you what I can do. When you break a magnet in half, do you get 2 small magnets? True or false? Naturally occurring magnets in nature, are there rocks that are actually naturally magnetic?
Yeah.
And if so, well, they do exist. Are they called plastics? Are they called stones? Are they called lodestones? Or are they called polar stones?
A lodestone.
Does anyone know?
That's a hard ass. Naturally occurring magnets.
Naturally occurring magnets.
I didn't know there was such thing.
There is, and I'll show you some.
Because sometimes you can walk and your compass will attract the lodestone. Or what is the stone? And then you go the wrong way.
Iron, steel, ferromagnetic items. Naturally occurring magnets are called plastic stones, lodestones, or polar stones. Yeah, you're going to pretty much have to guess that, aren't you?
Yeah.
Which of these is not needed to create a simple electromagnet? Which one can you do away with? A battery, a bulb, a copper wire, or a nail? Which one of those things can you do without if you need to create an electromagnet? That's what I got. Let's finish this up.
Tally it up.
Is that the last one? Is it?
Yeah. Let's say, yeah. That's my good. That's my good.
Okay, well, let's just stop the assessment,
Tally it up.
and then we'll go back.
Let's go. See what I did.
How'd we do?
I got 100%.
100%? Yeah, pretty easy, eh? So, it turns out you do know some stuff about magnets already. So yes, it is called magnetism. Magnets do have a north-seeking pole and a south-seeking pole. That is true. Two of the same kinds of poles repel each other. That is true. Opposite poles do attract each other. It's called a magnetic field. Remember the field concept? The further apart they are, they're getting stronger.
No.
No, they're getting weaker. And in fact, it follows the inverse square law. And yes, when I take a magnet and I break it in half with my bare hands, I get 2 small magnets. And if I were to take those 2 small magnets and break them apart with my bare hands, I would get 2 more small magnets, and so on. Naturally occurring magnets are in fact called sea lodestones. And I have a little box I will show you very soon. Some naturally occurring rocks. When I was in Greece, I picked up a rock that looked to me like a lodestone. And so I put it back, but it somehow inadvertently ended up in my shoe. And when I returned to Canada, I, of course, had no way of returning it. So I checked to see if it was magnetic, and it was not. So I was disappointed.
Where did it get in
'Cause
your shoe?
I don't know. I think someone must have put it in
Have you
there.
ever seen Apollo 18?
Apollo 18?
Yeah.
No. But the one where they go to the moon and there's actually...
The rocks on
Oh, yeah. Which of these does not need to create a simple electromagnet? The answer is
drop or black.
B, the bulb. You don't actually need the bulb. That's just there to tell if the current's going. All you really need, in fact, actually, anybody answer D? You could get away with D as well. Anybody answer D?
I answered B.
Yeah, I'd take D as well.
Give us
Oh, let's watch a video. I wonder what it could be about. You have 2 handouts here. One says magnets and magnetism. This is sort of one of those, you're going to have to skim through it and answer some questions kind of on your own kind of. Okay, so there are some things there that I'm going to expect you to know. Many of these things I will be talking about in the next couple weeks. Okay, I'll have to decide whether or not we're going to actually have a test on this run. If we do, it probably wouldn't be like a full-size test. It would be like a half test or something. Okay, there'll be some. Now, it's crunch time, you guys. There's no doubt about that. So we need to keep our foot on the gas kind of. I would like to, I've only got a few minutes here, but I'd like to talk about new clues to the Earth's magnetic flip-flops, okay? So I could spend a little time going through that. Now, it turns out, you probably know that the Earth has a magnetic field. I'm hoping you do, right? Okay, so here's the Earth, and in fact, the magnetic field of the Earth kind of looks like that. It kind of looks like, you know, a cartoon character kind of, right? The North Pole, which way is north way? Right in the room. North is that way, right? Okay, so we got your North Pole, we got our South Pole. I don't have my globe in here, but it turns out that north has not always been north. North has not always been north. So let's just read about these magnetic flip-flops. They're not flip-flops that magically stick to your feet. Next time the Earth's magnetic field flips, compass needles will point south instead of north. But scientists can't say when it will occur, and until now they've disagreed on how long the transitions take. A new study pins down how long it took for the last 4 reversals to play out, and also finds that the dramatic turnarounds occur more quickly near the equator than at higher latitudes closer to the poles. That means that folks living during the next reversal, which some scientists speculate might actually be underway right now, will see compasses change and behave differently in different locations, said study leader Brad Clement of Florida International University. Now you'll notice on the right-hand side there, you'll see a picture that's kind of fuzzy. You got South America on the left, Africa on the right, and what's down the middle there? Can you read it? Mid-Atlantic Ridge. Now that's exactly what its name suggests. It's a ridge. Here's South America, right? And here's Africa. And down the middle of the Atlantic, there's a, hence the name, the Mid-Atlantic Ridge. Okay? Now you're probably familiar with the idea of continental plates, you know, that whole Pangea stuff, continental drift and all that, right? Okay, so it turns out that South America is actually moving that way, west. And it turns out that Africa is actually moving that way. You ever notice that South America and Africa sort of look like they could have been pieced together at one time? Sort of have that shape, right? So that's the case. So what do you think's happening down the middle of the Atlantic? If you're pulling these two things apart, what's happening there? It's a ridge. It's like a big mountain range underneath the water. There's actually fresh rock. There's actually lava that's coming out on either side. Okay, there's volcanic activity under the water, and all this lava is pouring out on both sides. Okay, and that's sort of what's pushing the continents apart. So, Earth's magnetic field, I'm reading here again. Earth's magnetic field is thought to be generated deep inside the planet. An inner core of solid iron is surrounded by an outer core of molten iron. They rotate at different rates, and the interaction between the regions creates what scientists call a hydromagnetic dynamo. It's something like an electric motor, and it generates a magnetic field akin to a giant bar magnet. The process is not completely understood. In fact, one study suggests that the Earth's mantle, which surrounds the core, also plays a role. However it works, the setup has been in place for at least 3 billion of Earth's 4.6 billion years, science figure. But the field is shifty, periodically growing stronger and weaker, moving around, and even flipping its polarity entirely. In the past 15 million years, there have been 4 reversals every 1 million years, or about 1 shift every 250,000 years, climatically. The last one, however, was 790,000 years ago. That might suggest that we're long overdue for a big change. Not necessarily so, Clement says. The flips are not periodic, meaning that they don't adhere to a schedule.
Excuse the interruption, but with the owner of a turquoise Pontiac Wave, license plate number.
All right, so as I was saying, it would appear that we might be overdue for change, but it's not necessarily periodic. The intensity of the magnetic field has been dropping for the last 2,000 years, and it has dropped significantly during the past 2 decades. One recent study shows the decline in strength amounts to 10% over the last 100 years. So it's, on the surface, it certainly appears that we are undergoing a magnetic field shift. Do you feel it right now? No? How the heck do you think they know this? Some scientists speculate that a reversal is underway. Clement says that's like forecasting that the bottom will drop out of the stock market because it's gone down the past few days. We just don't know, he said. Researchers also have not known how long it takes for the magnetic field to make a transition. Studies have suggested anywhere from 1,000 to 28,000 years are required to initiate and complete a reversal. So you are not going to see in your lifetime, oh, all of a sudden your compass is pointing the other way. It's not going to happen. Okay? It doesn't happen that fast. I'm going to explain how they know all this right away. Okay? It's generally accepted that during a reversal, the geomagnetic field decreases to about 10% of its full polarity value. After the field is weakened, the directions undergo a nearly 180-degree change, and then the field strengthens in the opposite polarity direction. A major uncertainty, however, has remained regarding how long this process takes. Clement examined sediment cores gathered from deep ocean sites in a National Science Foundation program. The cores provided readings at multiple sites for the past 4 flips. He found that each took about 7,000 years. Interestingly enough, however, there is significant variation depending on the latitude. So I'm going to just explain some here how they know this. Okay, so here's South America. Here's Africa. I'm sure you're going to be looking sideways, right? So here's like the continental shelf, ocean, continental shelf, continent itself. And here's the ocean. Okay? So down the middle, they got this ridge. And it's sort of like a double peak kind of thing. And the lava is spewing out on either side like that, right? And so what you've got is these magnetic stripes along the ocean floor here. Okay, and remember that the continents, the plates themselves are moving this way, right? So as the lava flows out, okay, it creates a new sort of floor here, and then those plates are actually moving apart. I think it's about 2 centimeters a year outwards. You need to see me, Jordan?
You need a USB stick.
Oh, you need a USB stick. So what happens is you can actually make a magnet, like because the rock is very soft, it's molten lava. It's very susceptible to adjusting its magnetic field. So right now, if this way is north and this way is south, you're going to actually get, because remember, opposites attract, you're going to get a south pole there and a north pole there. The south pole of the magnets are going to point towards north. Okay? But when there's a flip-flop, when the pole is no longer north up there, right, and it's turned into south, then what, if this was back in time, what would this stripe be? Well, this would be a north, and that would be a south. And then when another flip-flop had occurred, well, then that's going to be south, and that's going to be north. Okay? So they can tell, knowing how fast those plates are moving apart, they can figure out, depending on how wide these stripes are, right? So what they've done is they've dug down into the rock, pulled out some samples, and figured out which way is it magnetic field pointing kind of thing. They can tell by how wide they are, knowing how fast they move, how long it's taken for that reversal to, or how long the Earth's magnetic field has been in that orientation. There's several of these stripes at the bottom of the Atlantic Ocean. That's how they know that the Earth's magnetic field is changing. That's kind of cool. When you agree, Mike?
Yep.
Yeah. That's kind of cool.
Can you use your compass over the Atlantic Ocean?
Can you use your compass over the Atlantic Ocean? Absolutely. I mean, they're a long ways down, right? These are rocks that have become magnetic because they are soft. The rock is able to flow, and so they are adhering to the Earth's magnetic field. That's what's happening. Okay? So I'm just going to read here where it says which way is up, and then we'll be done for the day. It takes less time, around 5,000 years, for the reversal to occur at lower latitudes. It takes longer, about 10,000 years, for the flip to play out near the poles. So in other words, the stripes are a different width at the poles. Not only would compasses gradually do a somersault readings, but Arctic dwellers would see changes that wouldn't match what tropical observers would note across the generations. So in other words, for people living in the far north, north would be that way. People living close to the equator, north would be the other way at the same time. Nobody understands how the shift occurs. Perhaps Clement says the magnetic field shrinks to essentially nothing, leaving several mini poles at the surface before the main poles rebuild on opposite sides of the world. Scientists have plenty of reasons to seek a better understanding. For one, the magnetic field lines extend out beyond Earth's atmosphere and provide the first line of defense against strong solar storms. And Clement wonders how the reversals might affect navigation by migrating birds and other animals that key in on the magnetic field to find their way. But 7,000 years is probably enough for them to adapt, he said. Clement has demonstrated that magnetic field reversal events occur within certain time frames, regardless of the polarity of the reversal, said Carolyn Ruffel, Program Director at the National Science Foundation's Division of Ocean Sciences. The study is detailed in the April 8th issue of the journal Nature. The work is an important contribution to our understanding of magnetic field reversal on our planet, said Ron Romero, Professor of Geophysics, blah, 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 blah. That's actually from 2004. Okay, so has there likely been changes in the Earth's magnetic field since 2004? Quite likely. Quite likely. Yeah. Okay. All right, so you should have kind of an understanding of what this diagram represents. At the very least, you should know that there are stripes on the Earth's, on the floor underneath the Atlantic Ocean that have magnetic and south reversal. That's very sort of bare minimum to each know. All right, that's good for today.
Got my brain.
Okay.